everyone. Today we present our work, M3imic, learning a versatile whole-body controller for multimodal motion mimicking. Humanoid whole-body control is a key pathway for legged robots to achieve human-like motion capabilities. Existing approaches mainly learn motion patterns from diverse human motion data to acquire flexible motor skills by motion tracking. Current input methods can be divided into two categories. The first is IK-based single-modal commands, which map different modalities into the robot joint space, such as the twist approach. The second is vectorized command space, which concatenates multiple modalities, learns a teacher policy with privileged observations, and distills it into a student policy using local observations, such as hover. The first category focuses on motion imitation but overlooks how input modalities affect deployment. The second struggles to capture cross-modal relationships. Thus, a key question arises: does input modality choice significantly impact real-world controller performance? To investigate this question, we design a unified multi-modal implicit command representation that can consume different forms of references. This representation allows us to systematically compare modality effects while maintaining a shared backbone. Built upon this representation, our framework mainly includes three stages: data preprocessing, policy training, and deployment. First, we collect human motion data and perform two preprocessing steps. We remove noisy and redundant sequences to improve data quality, and then retarget human motions into a standardized multimodal dataset for policy learning. In the training stage, we design independent encoder-decoder structures for three reference modalities: end-effector, human motion, and robot joint. Each modality has its own encoder for feature extraction and decoder for signal reconstruction. This modality-specific design preserves unique motion characteristic and provides better representations for unified whole-body control. After extracting latent feature commands, we combine them with robot proprioception signals. An action decoder then generates the robot action at each time step. The policy is trained with reinforcement learning, using curriculum learning to gradually improve task difficulty. The final stage is policy deployment. The trained model can directly support motion tracking and teleoperation tasks without additional fine-tuning. To answer the question we posed earlier, we conduct controlled experiments comparing policies trained with different reference modalities. The policy trained with end-effector reference, stronger robustness than that trained with robot joint reference. We attribute this to kinematic underdeterminacy. This is further supported by the fact that human pose input performs similarly to robot joint input. We used two representative human motion datasets, LUFN1 and 100 style, to evaluate in-domain informant and analyze how different modalities affect whole-body control. We further evaluate real-world teleoperation in out-domain scenarios. Without fine-tuning on any teleoperation data, these experiments directly measure transfer capability. Previous humanoid motion control methods rarely studied cross-scenario adaptation, especially when the deployment environment differs from the training domain. Our results demonstrate strong out-of-domain teleoperation ability and the robustness of our method. We collected some common movements, such as walking, jogging, walking backward, squatting, and other poses. You can watch our demonstration results. Thank you for watching.